Hola, soy Michael, and I don't speak like a Spanish, so this talk's gonna be in English. Thank you for coming to my talk, weighing in on issues with cloud scale, hacking the Withings WS-30, and a little bit about myself. As was mentioned, my name is Michael Coppola, and I've likely rooted your phone. I'm an undergrad at Northeastern University in Boston, United States. I play capture the flag games every now and then. And if you want to see more about this research and more about other things I've done, my website is poppopret.org. And a little bit about this presentation. We're going to be all over the place. We're going to be doing some software. We're going to be doing some hardware stuff. And I'm not just going to talk about the things I did correctly. I'm going to talk about the mistakes that I made and the failures that I had. And luckily, or hopefully, people can take away from this talk and take the experiences that I had and apply it to their own projects. I'm going to talk a little bit about the tools that I developed in order to do the things I needed to do. And as well, I'll talk about the techniques that I used in order to get what I needed. So what is a Withings WS-30? Basically, back in the day, you had a bathroom scale. You stepped on it, you got your weight, and you moved on with your day, but that's no longer the case. You put your scale in the cloud, and you get this thing called the Withings WS-30. And what good talk would be without a narrative? We're going to have a little story here. You, the audience, are going to put yourselves in the shoes of a United States cyber command agent tasked with protecting the nation's infrastructure. And what greater threat to America is there than North Korea? North Korea is a little crazy. Kim Jong-un is their leader. And what we want to do is we want to infiltrate North Korea. We want to get inside the network and basically get some intel. We're going to have to see how exactly we're going to do this. And one thing that we notice working for the government is that Kim Jong-un is just so fat that he's so concerned about his weight that he always carries this scale with him. So he carries it everywhere when he's out with his girlfriend, even in the middle of ceremonies. It's just ridiculous. So if we want to get real close to Kim Jong-un, see what's up with North Korea, we're just going to have to get into this scale, no matter what. So we're going to have to build an attack profile. What attack surface is there on this thing? There's Wi-Fi and there's Bluetooth, how it does this wireless communications. There's not only the driver, but the actual application that's dealing with the data coming in over that interface. There's network communications itself, so the actual data that's being sent over the wire. And as mentioned before, the actual parsing of the input that's coming in over these interfaces. The one thing about this device is that there are actually no listening network services on it. So it's not like you can just connect to a server and send bytes and get a shell. You're actually going to have to wait for this thing to connect out to the world, and you're just going to hope to be there when that happens. One thing that really drew me to this device in particular is I looked in the frequently asked questions of the scale, and you can see right there it says it does firmware updates automatically over the internet. And if you're like me, this is a big red flag going off. There's no way in hell that they did this correctly. So this is going to be our way in, most likely. So what we want to do is just figure out how this thing is doing its firmware updates. So we're going to wait until night, or we can press a button to initiate it manually. And basically, the first thing that we have to do is we have to actually push a wireless profile to it. So we do this over Bluetooth after we pair it with our smartphone. And the first thing it does when it does a firmware update is it connects, or it sends a DNS request to scalews.withings.net in order to find out where the company server is. And it talks over a plain text HTTP session using a JSON-based protocol. What it does, the first thing it does in the session is it connects, or it creates a session using challenge handshake authentication, which basically means that there is a pre-shared secret on the device and the server. It's an unknown key that both know, but a party that's doing a man-in-the-middle attack would not know what that key is. The device, the scale is going to connect to Withings, and it's going to say, hey, I want to connect, and Withings is going to reply saying here is a nonce value, a random bunch of bytes, and then you have to hash that nonce value with your pre-shared key with a bunch of other values, which we can likely assume that are going to be the values in this post request that we're replying to, and it's going to return the hash. And if the server says, okay, this hash matches with the hash that I calculated on my own, then I'm going to authenticate you. What our ultimate goal is to get the firmware image so we can reverse engineer this thing. And what we want to do is perhaps, if you saw and looked at the actual request that we made in reply, there's an auth variable, there's the actual hash variable, and you see there's current FW, which we can make a reasonable assumption is a current firmware version. So maybe we can make the assumption that if we get control over that authentication step and send it a firmware version that's lower than 2.11, then maybe it will initiate some sort of update because it will realize that it's out of date. The problem is that we don't have that pre-shared key of our own. The scale knows it, but we don't, so we can't complete the authentication without having the scale actually present. So the easiest way to set up a man-in-the-middle attack and actually try to figure this out is to just do DNS spoofing. Makes that initial request. We are just going to force it to connect to our DNS server rather than the world's, and we will send back an IP address on the local LAN, and it'll connect to us. The way that we actually do this is we have the scale connecting to us, where it's going to say, I want to create a connection. And then once it connects to us, we're going to connect to Withings and say, I want to create a connection. Withings is going to return a nonce value to us, and then we proxy it over to the scale. The scale hashes it appropriately, gives us the hash, and we push the hash over to Withings. So we never actually need to know the secret. We're just acting as an intermediary, except when we push the actual hash to the server, we're going to do that, and we're going to change the 2.11 to 2.10 and just see what happens. And we do that, and this is the response that we get. You can see in BLC, the BLC section of this JSON blob, there's a URL that says fw.withings.net/wbs03_211.bin. That is the firmware image, and now we can start actually reverse engineering it. So the first thing we do is we run a tool called binwalk on it. Binwalk is written by the guys at a site called devttys0.com. And basically, it checks the entirety of a file for all possible headers that might be inside of it. If you've ever used the file command on Linux, it basically runs that at every offset, plus an additional database of headers that's specific to binwalk. But we realize that we don't get any results when we do that, so we're actually going to have to reverse engineer this thing for real. One thing that we notice is that there are actually lots of ASCII strings in here. They're not only they're not encrypted at all, they're not compressed at all, because we just get a whole bunch of them back. So that's good news for us. It means less work that we have to do to actually get the final result. Another thing we notice is that there are multiple null-padded sections in this blob, this giant binary. So there's a bunch of bytes, and then there's a bunch of zeros, and then a bunch of bytes, and then a bunch of zeros. So we can make an assumption that it's not just one object that's in this binary, but there's multiple objects that are just stuck together and padded to some offset that it needs to be at. We just do a cursory look at the header of the file. The first 4 bytes is an integer that we realize is just representing the size of the file itself. And other assumptions we can make, such as the we see OXD3, which is a hex for decimal 211. We can make the assumption that that is a firmware version of this firmware blob. As well, there's the next 4 bytes is OX28, and we can make another reasonable assumption that that's some offset that is meaningful. So let's make another assumption, since we seem privy to doing that. That offset is the beginning of the actual code in the firmware image. So now that we know where the code starts, we have to figure out, well, what code is it? So we do this by ripping open the scale and identifying the actual microcontroller. By looking at the serial number on the actual microcontroller, we see that it is a Freescale Kinetis K20 family, just by Googling for the serial number. And by looking at the data sheet, we see that it's an ARM Cortex M4 chip, which means it's running an ARM v7 instruction set. So it's using thumb2 instructions rather than ARM or thumb. now that we actually figured out what code is there, we want to see where all of the code blocks are. So there are a couple different ways you can do this. You can just open up IDA, stick your cursor in the middle of a bunch of bytes and just press C, and hopefully it disassembles to something that's meaningful. You can be a little smarter about it too. You can check to see if you're disassembling ARM code, then every 4 bytes, ARM instructions are always 4 bytes long, and there's a high probability that the first nibble of that instruction is going to be OXE. As well, there are certain compiler conventions such as since ARM instructions are always 4 bytes long, there's this concept of alignment. So everything needs to be at a 4 byte alignment. So if there's something that's 2 bytes and they need to reach those 4 bytes, they're just going to put padding there. The compiler for the code on the scale always use OXBF00, which coincidentally disassembled to a NOP and thumb code. But I've seen other compilers that put OX00 there instead. Also, if you want to be even a little more smarter about it, you can use global references in the binary to figure out where the actual functions are exactly. For instance, we can scan through the binary and find where there are ASCII strings, and then byte search for pointers to those. So once we find where the pointers are, the way that ARM compiles functions, it puts pointers to the data at the end, and then they use internal local references to reference those pointers, which then they use to reference the global data. So if we find a bunch of strings and then we find pointers to those strings one after another, we can make the assumption that if you disassemble backwards or upwards, then you're going to start finding code. So we do this and we find strings and we search for them, but we realize that when we start disassembling the actual code itself, all the global references are off, even though the code looks completely meaningful and totally correct. But anytime you have a string, it just references the middle of the string and not the beginning or anything that would actually make sense. So there's this concept with binaries, it's called a base address, which means that binaries usually aren't placed in memory at the OX or at address OX0, but it's usually at some point in memory. And we have to find out exactly where that is in order to line up our position-independent code so that it references the global data correctly. So what I did was I wrote a script called basefind.py, and it's basically a couple lines of Python that just takes the binary, scans through for all strings, and then automatically places the binary at every possible base address, and then checks to see the global references to see if all those pointers actually point to the beginning of an ASCII string. And obviously, if you go through and treat every 4 bytes of a file as a pointer, a lot of them aren't going to match up. But if you do that for every possible offset, the one with the most matches is very likely your base address. So we run this quickly, and we see that a base address OX4000, there are 2,170 hits, where there are actually pointers in the file that point to the beginning of an ASCII string. So that means that we rebase it at OX4000 and everything lines up. And now we can start actually reversing this. Little cute thing that I found is that as I started reversing the binary, there was this all debug strings and all like user paths that were in there always referenced this username called fdusanter. And we find that that's actually one of the developers of the firmware. And if you Google that name, we find his email, and we start pulling docs. We find an advertisement that he's selling a home in China. So, not that it's super important, but it was just a little fun tidbit. Anyways, we start reversing this thing, and we find out all the different sections of the binary. For instance, whenever it wants to make an HTTP request, it uses libcurl, and whenever like the actual TCP/IP stack that it uses is LWIP, and they chose those 2 libraries specifically because they're not GPL. So usually, if you're reversing something and you find any hint of GPL code, then you can try to send a GPL request and get source code, but we can't do that for this case. They also wrote a bunch of custom services. Withings wrote a bunch of custom services. For instance, there's dblib, which basically acts as a local database of key values. The WS-lib, which is an abstraction of the HTTP of libcurl in order to interact with the Withings website, and other things such as managing connections or users on the scale. Um, the most interesting library is the dblib, where it actually stores data that we might find interesting. And if you find, we realize that in order to initialize something in a database, there's the dblib init element function call. And then in order to grab something from the database, there's the dblib get element function call. And by reversing out every single reference to this call and figuring out what exactly is being done with the data it retrieves, we can start to reverse out the entire database. For instance, we see things like MAC address, which is size OX12. So there's the bytes that represent the device's MAC address are stored in this database. The host name that it needs to connect to in order to reach the Withings servers. And then there's this thing at number 3 called secret. And that just sounds really interesting. I like secrets. I'm sure you guys do too. So maybe this is the secret, the pre-shared key that it needs in order to do the challenge handshake authentication to establish a connection with Withings. The interesting thing here is that every single one of these elements, 1 through 38, or at least the ones I was able to reverse out, they all have a matching dblib init element to initialize the initial value, except for secret. Secret never has an initializing value, so we have to figure out where did it come from. We can see just quickly how it's actually being used and to confirm our assumption that this is the pre-shared key. If we reverse out, and if you have hex arrays, it makes everything very nice. We decompile these the firmware into C code, and we see that it does dblib get element number 3 of OX11 bytes. We get our secret, and then we concatenate it with a few other things. Let's see, what is it? The MAC address and the nonce value that it received from Withings. And once it runs it through an MD5 routine, it sends back that hash, and that's how it completes the authentication. Other things we can do as we continue reversing out the firmware is actually figuring out what are the other values in this firmware header. We made a couple assumptions, and we actually realized that our assumptions were correct. The first 4 bytes is the size, and our firmware version is the correct. And that OX28 is actually a correct assumption as well. That is the address of the beginning of the actual binary running the scale. And also our assumption that there are multiple objects padded, that were null padded together is also correct, because we see that there's the kinetis, which is the actual main code running on the scale, and also there's Wi-Fi and Bluetooth firmware that's also packaged in. So when you do a firmware update, you're not only updating the scale, but you're updating all the code on the chips. And also at the very end, we see the CRC, which is the last 4 bytes of the file, which we can actually reverse out and see that that's the checksum for the entire firmware. So if we want to create a firmware image with our malicious code and send it out to the scale in order to get code execution on it, we need to make sure that we do that checksum correctly. And we reverse out, we see there's an init CRC32 routine where it talks to peripheral registers in the microcontroller. Basically what it does is it reads and writes to really, really high addresses, and the microcontroller intercepts those writes and says, oh, this is a magic address for initializing the polynomial for the CRC. So when we write to this really high address, we're going to write these bytes, and it's going to initialize the CRC routine with that. And by looking at the data sheet for the microcontroller, we can reverse out exactly what each address is doing, and then we can do the same CRC routine locally and construct our firmware image appropriately. Thus, I wrote a program called image checksum, which basically you can modify a firmware image as however you wish, and then you pass it through the routine, and it patches in the correct checksums and pops out a binary. And you can see here we're actually reflashing the scale with our binary, and we now have code execution on the device. So that's cool, but really what's even cooler are exploits. So we want some delicious 0 day. Unfortunately, by this point, I was already about a couple months into the project, and I was starting to get more interested in other things. I have this bad habit of jumping between projects. So I didn't explore this as much as I wanted to, but I'll explain the steps I took to get close to that. So in order to actually find some bugs, there are a couple different ways we can do it. Just using IDA-Pro, we can statically analyze the binary and by hand, and we can find bugs and then write exploits that way. Or we can take the automatic route and fuzz it. So we just send it random data until it crashes and figure out how it crashed. So the easiest way in would probably be the actual connection to the Withings server, so we don't have to deal with any driver code or anything that's really obscure like Bluetooth pairing. But we'll actually just see it makes a connection out to Withings, it receives values back and then parses them. So maybe if we send it back corrupted values there, then it'll crash somehow. So we can either send it improperly formatted JSON and crash the JSON parser itself, or maybe we'll just send it garbage values and properly formatted JSON and crash the code that's dealing with those values. If we're actually going to fuzz this thing, and if we actually do crash it, we're going to need introspection or a debugger on it to see how it crashed and how we can make it into an exploit. So the first thing we check for is a debug console. Is there an already built-in way to debug this thing because the developers needed one? And we do see that there actually is a debug console built into it. If you look towards the top of the firmware image, there's an array of a pointer to the handler. Basically, it acts as a shell, and there's a bunch of commands implemented in here. So there's a bunch of pointers to the functions themselves, as well as a pointer to the name of it and a pointer to a description of the command. And we can access the shell over UART, or basically a simplified serial connection. And in order to find out how to solder into the microcontroller to access this UART console, we need to look into the datasheet to see which pins we need to tap into. Unfortunately, it's not quite so simple. We look in the datasheet, and there's this register called the port control module. And basically, the value of that register specifies the configuration of the UART pins on the microcontroller. And there are, I believe, there were 7 different potential states that the port control module could be in. And depending on some other setting, it kind of multiplied that into 35 potential configurations that the UART pinout could be. So I tried to solder around on it. I tried the first couple ones that seemed apparent, and I just couldn't find the damn thing. And then, like a month into the project, I finally flipped the board over for the first time, and you can see pretty plainly there's 4 solder pads: TX, RX, RTS, CTS. Yeah, that's UART. Fuck me. But obviously, that would just be too easy. You solder into it, and there's no signal on there. So, whatever. I don't know if it was just because my oscilloscope was misconfigured, or if they actually disabled the UART, or if there was some sort of quote-unquote password where you had to pull a pin high or send it some bits. Oh wait, we have it. So the fact that we have code execution on the device already sort of solves a bunch of problems. The way that ARM works is that it keeps it keeps a vector table somewhere in memory where if different actions happen on like from the hardware level, then it runs those handlers. So one of those handlers is called the hard fault handler. So if we do an invalid memory access, or if we crash it in some wild way, it's going to call into that hard fault handler. So why not just hook that hard fault handler so that any time we crash the device, it calls our code, and then we just take the current register state, push it over the wire using code that's already on the device, such as connect to the Withings server and push our register state, except we're not actually going to send it to them. We're man-in-the-middling it, and we'll keep it within our network. And then we'll sniff out the crashes. And then that way we can get some introspection into the device and see exactly what's happening. This is the code that I was going to use in order to actually hook the hard fault handler. You could see there's a lot of hard-coded things. For instance, I hard-coded the sprintf function as well as the wslib do HTTP post request function to the actual addresses that those functions are at in the firmware. And then once we call into the hard fault handler, we grab the register state and then push it over the wire, and then we'll be there to sniff it with Wireshark. The problem is that once we start changing code on the device, there's a very high chance that we're actually going to introduce a bug of our own and brick it. And there's also a good enough chance that we're going to brick it in such a way that we won't be able to reflash the device again. So we need a recovery plan. I did a talk at DEF CON last year doing some router firmware stuff, and there was a built-in recovery plan if you brick the device. It was basically a Linux box. It had a bootloader, and then it booted into a kernel. And you can interact with the bootloader over Ethernet or over UART right on the board. So if we sent it an invalid kernel image, the thing would brick, but then we could just break into the bootloader and keep reflashing it over and over at our will. The problem is that this is a real-time operating system. There's no bootloaders. There's nothing that we can break into if we brick it. It's just a binary running on the device, and if that binary is corrupt, we're not going to be able to get it off or get a new binary on. So how are we going to solve this problem? We need a recovery plan. Why not actually dump the flash memory and reprogram the flash memory itself on the circuit board with a new firmware image in case we brick it? So what we do is we take the top off it again, and we identify the flash chip. Just by Googling around for vendor names and serial numbers, we realize that there's a expansion chip that serves as the flash memory. And there are a couple different ways to desolder it. If you're super hardcore and you're a really elite hacker, you can just take a heat gun and tweezers and pop the sucker off. If you want to be a little more better about it, you can use a soldering iron blade tip. For instance, soldering irons usually have a pencil tip that goes to a point, but you can get tips that fan out to a large area, and you can put it on all the pins at once and take a side off at the same time. And if you want to be a little better about it, you can use solder wick, which is basically metal yarn, where it acts as a sponge. If you put it over solder and heat it up, it's going to suck up the solder right off. Or if you have like a couple $100,000, you can buy a rework station, which basically is super cool. But you basically bolt in your circuit board, and it has hot air going on the bottom and the top. And it raises the board to proper solder reflow temperature. And then once the entire board is basically liquefied, or the solder on the board is liquefied, a suction cup comes down and takes your, oh, fuck. Takes the chip off. All right. So anyways, I Sup? I've been watching, I came prepared. All right. let's continue, shall we? All right, and bring him back up. All right. So, like I was saying before I was so rudely interrupted, I thought that I was a super hardcore hacker, but that wasn't the case. I tried to use a heat gun and tweezers, and I learned the hard way. This is what it looks like when you do it wrong. Yeah, it sucks. See all that brown area? All right. That's the actual circuit board itself. That is not conductive. There used to be conductive material there. And all these traces that were lifted up, those are just fried right now. They're broken. So I walked around and I asked some friends and some coworkers, these things are kind of expensive. I don't really want to buy another one. So what can I do to fix this? Maybe there's some sort of repair that I can do. And I was told, yeah, this is a really easy fix. It's kind of bad, but it's not so bad. What you can do is use some solder glue and basically put some dabs in the exposed circuit board, and that recreates the solder pad. You can take some really, really thin gauge wire, strip off the coating, and thread it underneath the traces, and then solder them down, and that should work perfectly well. Just like, oh, okay. So I got some solder glue, I got some really thin gauge wire, and I fucked it up even worse. This is what it looks like when you fix it wrong. So I figured, okay, this board's toast, so fuck it, I got a new one. eBay to the rescue. So once I screwed up the first board, I then continued practicing. I took every single chip off for the heat gun and tweezers, so I made sure I wouldn't screw it up when I got the new one. And luckily, I did it right, and this is what it looks like when you do it right. I desoldered the flash chip there, and I replaced it with 8 pins sticking up in a standard adapter there, or whatever you call it, standard socket. And basically what this provides us is the ability to put the flash memory into its own socket and then pull it on and off the board at our will, and then put it into a USB programmer at our will. That way we don't have to desolder and resolder each time. So we put it into a socket, and we realized that it still works, everything's great, and we did it correctly. The check mark is good. And I didn't exactly have a socket that fit the exact chip. So if you notice, there's this big piece of plastic that is a socket, and the flash chip is hidden under there, and I put a bunch of a piece of junk plastic, and I wrapped it in rubber bands. And if you hold it just right and you have the right pressure on it, all the contacts touch and everything's great. So you don't need to have super crazy tools in order to do this. You just have to hack it together. And we connect it to the USB programmer after soldering some wires to, we have to solder a custom adapter to reach it. And we dump the flash memory and score. We look at the first few bytes. We see this thing that looks like a MAC address. And we see a bunch of hex digits, which looks like a secret. I don't know. We know the challenge format, so we concatenate the things together. We hash it, and we connect to the Withings server, and it authenticates us. Yay. All right, demo time. So I don't have a scale here, but I will show something else that I thought was pretty fun. When you have a scale and you step on it and it weighs you, it sends that data point off to the Withings server. So now that we have the ability to arbitrarily connect to the Withings server, and then we have full control over the session, so we can send it data points that we want rather than the ones that it measured. So let me just see if the internet is still working here. It's a little slow, but I think it should work. Use former interface. This was all this interface right here for the past year, and then they changed it a week ago. So I'm really glad that they still have this, so it still works. And what I did was I wrote a Python script called draw, logo, and we are going to connect to Withings, and we're going to send it a whole shitload of HTTP requests. So that goes and we flood the server. Does anybody have any questions? Cannot see anything. We'll just wait for this and I'll ask that later. All right, it should be finishing up. I think there are like 3,000 points on this. Just vodka, I think. This was Cunnington Pomelo. I don't know. It tastes like grapefruit. It's sugary. All right, we've refreshed this bad boy and see what happens. Awesome. All right. Slideshow. Cool. All right. So what did we learn from this? A couple things. One thing I learned was that ARM compilers are incredibly aggressive. They try as hard as possible to keep everything a relative reference. And what that means is that when you're running thumb2 code, you have, or when you run ARM code, there are different states that the processor could be in, such as ARM mode, and thumb2 mode. When you run ARM mode, you have 4-byte instructions. They're always 4 bytes, and they have the ability to reference anywhere in memory. When you're running thumb code, your instructions are always 2 bytes, and they have the ability to reference, I think, 128 bytes in any direction. And they try as hard to compile things such that it uses those really efficient relative instructions. So what they do is they have pointers at the end such that they reference those pointers and then dereference those. And, okay. And they try to inline everything as much as possible using this design, such that if you have a really, really long function, then you have a bunch of assembly, and then the actual data itself that you're referencing will be right after it, and then it literally just branches right over it, and then continues executing, which is completely different than x86, but it's actually kind of cool. Another thing I learned is that strings are your friends in every sense of the phrase. They help you find the base address if you treat them as global references. They help you find code blocks by finding the pointers to those strings. And the actual string, the contents of the strings themselves, they act as debugging information. They let you learn symbol names. They let you know the purpose of those code blocks and all sorts of debugging info that the developers themselves put in. And also, there's lots of help to be had from just looking at the documentation that the hardware vendors put online, the data sheets, which give deep technical detail about how the chip actually works. And they usually put reference manuals, which is, okay, we have this really convoluted technical specification, so here's a bunch of code that we wrote that does exactly what you need to do. And it just really helps. And also, a little thing I found is that embedded system security really sucks. So, thanks to some people who helped me throughout this, this project. And thanks to Withings, because they saw my talk and they sent me a free scale. So, good vendor. So, greets to some people as well. And we go back to our friend Kim Jong-un. And we get control over his scale, and we get control over his account. And what we end up doing is we steadily make his weight higher and higher and higher, and he just feels so terrible that he kills himself. Another one for America. Thank you, everybody. Anybody have any questions?
Thank you, Michael.